The night sky looks like an endless black ocean, and the most dangerous simple question you can ask is this: does the universe have an edge? Is there a final wall out there? Is there a place where everything just stops? The universe does not need a wall to limit us. It uses something far more subtle: a horizon. Not the horizon of land and sea, but a horizon made from time itself, a boundary drawn by the age of the universe and the speed of light. Once you understand that boundary, you understand why there are places we cannot see, cannot reach, and may never know directly. When people imagine the end of the universe, they picture a cliff. You travel far enough and you arrive at a rim. You look over the side and there is nothing. But the universe is not built like a room. It is built like a story told by light. You never see things as they are right now. You see them as they were, because light takes time to arrive. The moon is more than a second in the past. The sun is more than 8 minutes in the past. Many of the stars you see with your eyes are not showing you the present. They are showing you history. And once you accept that, the idea of an edge changes. The true limit is not space. The true limit is information. There is a distance so vast that light from beyond it has not had enough time to reach us since the universe began. That is not a poetic idea. It is a physical consequence. The universe has an age. Light has a maximum speed. Put those two together and you get a sphere around us, an invisible bubble of everything that could possibly have sent a signal to us so far. This is the observable universe. It is not the whole universe. It is the part of the universe that can be in causal contact with us. Now comes the twist that makes the idea of an edge feel even stranger. The universe is expanding, not like galaxies exploding outward through a static emptiness, but like space itself stretching between galaxies. The distance is not just large, the distance is actively changing. That means there are regions so far away that even if their light began traveling toward us long ago, the expansion of space can keep pulling those regions away faster than the light can close the gap. In those cases, it is not simply that we have not seen them yet. It is that we may never see them, not because of weak technology, because of the geometry of space-time and the way expansion works. This creates a second kind of horizon, a cosmic event horizon. A boundary beyond which events can no longer affect us, even in principle, if the expansion continues the way it appears to be continuing. The universe does not end at that horizon, but our access to reality ends there. The edge is not a place, it is a condition. And this is where the story becomes unsettling in a very specific way. You can build a bigger telescope, you can collect more light, you can place your instruments in deeper cold. You can sharpen your measurements until they feel almost supernatural. You still cannot break the speed of light. You still cannot rewrite the age of the universe. Eventually, you run into a limit that is not engineering. It is physics. But this does not make the universe meaningless. It makes it more honest. It tells us there is a portion of reality that will always lie outside the page we can read. Not because we are not smart enough, but because the book itself has a bound. If you want to feel this in your bones, imagine a swimmer trying to reach shore while the river gets faster and faster. The swimmer can be strong. The swimmer can be determined. But if the current increases beyond what a swimmer can overcome, there will be a point where moving forward no longer reduces the distance. That is what expansion can do to light over cosmic scales. Light is not failing. It is obeying the rules. The rules are what create the horizon. So when we say the universe has an edge, we are really asking a deeper question. Is there a boundary to existence or only a boundary to what can ever be known? And if there are regions we will never see, how do we infer what might be out there using only the clues left inside our observable bubble? Because that is what science does at its best. It does not just stare into darkness and hope, it looks for fingerprints. If the universe has a shape, if it has curvature, if expansion has a history, if the earliest light carries a pattern, then those patterns are not just pretty. They are evidence. They are the only way to talk about what lies beyond our direct reach without turning it into fantasy. And this is where the story begins to lock in. The end of the universe is not the end of space. It is the horizon of information. The question is not where the edge is. The question is, what kind of universe creates an edge like this, and what that edge can tell us about everything we cannot see? From here, we follow the methods that turn this into something measurable: ancient light, the cosmic background, the large-scale structure of galaxies, the expansion rate, and the uncomfortable fact that the universe may be far larger than the part we can ever observe, while still leaving enough evidence inside our horizon to let us reconstruct a story about the whole. There is a point in deep space where your telescope stops seeing stars and galaxies and starts seeing something far stranger. A kind of light that does not come from any star at all, light that fills the entire sky, coming from every direction with eerie uniformity, like a faint glow behind everything. This is the closest thing the universe has to a hard visual boundary. Not a wall in space, but a wall in time. When you look far enough away, you are not just looking across distance. You are looking back into an era when the universe itself was different, hotter, denser, more violent. Not violent in explosions you could watch, but violent in the sense that matter and light could not travel freely. The universe was not transparent, it was a fog. Early on, space was packed with charged particles, free electrons, and nuclei, and light could not move through that environment without being constantly scattered. Photons were trapped in a crowded swarm, bouncing and bouncing and bouncing, never getting a clear path. If you had eyes back then, there would be no stars, no darkness, no depth, just a blinding uniform haze everywhere. Then, as the universe expanded, it cooled. Eventually, it crossed a threshold where electrons could finally settle down and bind to nuclei, forming neutral atoms. The fog lifted, space became transparent, and at that moment, the trapped light was suddenly free to stream outward in straight lines for the first time. That ancient released light is still traveling today. But the universe has stretched since then, so the light has been stretched too, pulled into longer and longer wavelengths until it became microwave radiation, far beyond what human eyes can see. It is called the cosmic microwave background. It is not a theory. It is a sky you can measure, a leftover glow from the first time the universe became clear. And here is the key. When you point a telescope to the edge of what is visible, you are not seeing the edge of space, you are seeing the edge of transparency. You are seeing the oldest light that can possibly reach you, because anything earlier than that was trapped in the fog. That is why this boundary feels like a surface. It surrounds us, not because we are special, but because we sit inside our own observable bubble, and the oldest light we can receive comes from a spherical shell of last scattering around us. People sometimes call it a wall, but it is not a wall made of matter. It is the surface where the universe stops being a clear window and becomes an opaque memory. The farthest view is the universe's baby picture. Now, the baby picture is not perfectly smooth. It has tiny temperature variations, slight modeling, subtle hot and cold patches. Those small imperfections are everything. They are the seeds of structure. They are the original faint blueprint that gravity will later amplify into galaxies, clusters, and the cosmic web. In a sense, every galaxy you have ever seen is a grown-up version of a tiny bump in that ancient light, and this is where the idea of the end of the universe becomes more slippery. Because the universe has at least two different kinds of edges. One edge is what we cannot see because the universe was opaque in the beginning. The other edge is what we cannot ever see because expansion can push regions out of causal contact, meaning their future light will never arrive, even if we wait forever. So there is a limit behind us, a visibility limit, the fog of the early universe. And there is a limit ahead of us, a causality limit driven by expansion. Between those two limits is the entire story of everything we can possibly observe directly, from the first free light to the last reachable galaxy. But the most unsettling part is this. The cosmic microwave background is not coming from a place, it is coming from a time. The surface you see is not fixed in space like a painted sphere, it is a horizon made from history. If you could move to another galaxy far away, that galaxy would also see its own cosmic microwave background surrounding it, its own version of the same early fog boundary. The universe does not have one edge. Every observer carries their own observable boundary with them. This is why the phrase, "the end of the universe," is almost a trap. It makes you imagine a destination, but what we actually have are horizons, and horizons are not destinations. They are limits of what signals can do, limits of what information can reach you, limits of what the universe allows you to know from where you are. And yet, physics is annoying in the best way, because even when you cannot see beyond a horizon, you can still learn about what must be beyond it by measuring the shape of what you do see. The patterns in that ancient light, the way the temperature variations are distributed, the way the geometry seems to behave. All of that can hint at whether the universe is flat or curved, finite or endless, smooth or slightly warped. The horizon hides direct sight, but it does not erase fingerprints. So the real game becomes this. If we cannot travel to the edge and we cannot see beyond it, then we have to treat the universe like a crime scene. We look for clues that cannot be faked. We look for patterns that only one kind of universe can produce. And the cosmic microwave background is the most ancient and most global clue we possess. Because it is not just light, it is a fossil, a snapshot of the universe when it was young enough that everything we see today was still only a whisper in the noise. There is another boundary that matters even more than the ancient fog, because this one is not behind us. It is in front of us. It is not a limit on how far we can see into the past. It is a limit on how much of the universe can ever reach us in the future, no matter how long we wait. The universe is expanding. That part is familiar. Galaxies are not flying through space like rockets. Space itself is stretching, and the distance between galaxy groups grows because the fabric between them grows. At small scales, gravity holds things together. A galaxy stays a galaxy. A local group stays a local group. But beyond that, the cosmic stretching wins, and the far universe keeps sliding away. For a long time, people imagined expansion as a simple coasting, like a thrown ball that keeps moving but slows. Then, measurements forced a stranger conclusion. The expansion is not slowing down, it is speeding up. Something is pushing space to stretch faster over time. We do not know what it is in a deep, satisfying way, so physics gives it a name that is honest about our ignorance. Dark energy. Dark energy is not a substance you can scoop into a container. It behaves more like a property of space itself, as if empty space has its own pressure, and that pressure makes new space appear. The terrifying part is that the more space you have, the more of this effect you get, which means the stretching can accelerate. It is a feedback loop built into the vacuum. Now, here is the trick that makes the end of the universe feel real. If expansion accelerates, there exists a distance beyond which light emitted today will never reach us, not because the light is weak, and not because it gets tired, but because the space between us and the source grows too fast. The light runs forward, but the floor beneath it stretches away faster than the light can cross it. The signal is not blocked by a wall. It is defeated by geometry. That boundary is called an event horizon. It is not a horizon like the Earth has, where you could travel and reveal more. It is a horizon in time, meaning it divides what can ever communicate with you from what cannot. Anything beyond that line can still exist, still shine, still explode, still form new stars, and still live out its cosmic story. But its story cannot reach you. Not later. Not eventually. Not ever. This is the closest thing modern cosmology has to a true edge. It is not an edge you can touch. It is an edge where information stops, and in physics, information is everything. If a region can never send you even one photon in the entire future, then for you, that region is not part of your reachable universe. The strange part is that this horizon is not a fixed distance like a fence. It is dynamic. It depends on the expansion history of the universe. In a universe that accelerates forever, more and more galaxies will cross that horizon as time goes on. They do not suddenly disappear in a dramatic flash. They fade, slowly, because their light gets stretched to longer wavelengths, and the signals become weaker and weaker. The galaxies look redder, dimmer, softer, until they become effectively invisible. This is not science fiction. It is the logical outcome of an accelerating expansion. The far universe is not simply far. It is leaving. If you want a brutal mental image, imagine standing on a beach and watching ships sail away. At first, you can see every detail. Then, you see only the shape. Then, only the mast. Then a dot. Then nothing. The ships did not hit a wall. They did not stop existing. They just crossed a horizon of visibility created by curvature and distance. The cosmic version is worse because it is not just a horizon of sight. It is a horizon of causality. Those galaxies are not just out of view. They are out of reach of the future. And that changes what the phrase end of the universe can mean. It might not mean the universe stops. It might mean the universe becomes unreachable piece by piece until what remains is an island of gravity, a small neighborhood that stays bound while everything else slips beyond the horizon. In that far future, if intelligent life still exists in some distant epoch, they might look up and see a sky with almost nothing in it. Not because the universe is empty, but because expansion has hidden the evidence. Their local group would be the only visible structure surrounded by darkness that is not a void, but a curtain pulled by geometry. They might have no easy way to discover the Big Bang at all, because the clues would be stretched, diluted, and pushed out of view. So the end is not one place. It is a process. It is the universe turning into many isolated regions that cannot talk to each other, each trapped inside its own horizon, each with its own last reachable light. The deeper question is obvious and uncomfortable. If the universe has a horizon that can erase the visible cosmos from view over time, then how can we ever know the full shape of reality? How do you measure something that will not let all its parts communicate with you? The answer is that you do not measure it by traveling. You measure it by reading the early fingerprints that are still here now, before they fade. That means the story of the end of the universe is also a story about a race against cosmic isolation. Not a race with rockets, but a race with observation, while the sky still contains enough information to reveal what kind of universe this is and what kind of edge we are living inside. If the event horizon is the future edge, then we also need to talk about the past edge, because that is the one we actually touch every time we look up. This is the boundary of the observable universe. It is not the end of everything. It is the end of what light has had time to bring to us since the beginning. The universe is about 13.8 billion years old. That sounds like a simple number, but it hides a weird consequence. You might think the observable universe should be a sphere with a radius of 13.8 billion light years, because light travels 1 light year per year. But the universe has been expanding the whole time the light was traveling. So the most distant things we can see today are much farther than 13.8 billion light years away right now. That is why cosmologists say the observable universe is roughly 93 billion light years across. It is not that light broke the speed limit. It is that the ruler we measure with has been stretching while the light was on the road. This gives us a clean definition of one kind of cosmic edge, the particle horizon. It is the maximum distance from which any signal could have reached us since the beginning of the universe. If something is beyond that horizon, it might exist, but it has not had time to affect us. It has not had time to inform us. It is outside our visible history. Now, here is the part that makes the phrase "end of the universe" slippery, because there are at least two ends already. The particle horizon is the edge of what we can see from the past. The event horizon is the edge of what we will ever see in the future. They are not the same boundary, and in an accelerating universe, they do not even move the same way. And there is a third edge that feels like a literal wall, the cosmic microwave background. This is the oldest light we can see. It is not light from stars. It is not light from galaxies. It is the afterglow of the early universe itself. Long ago, the universe was so hot and dense that matter existed as a glowing plasma. In that state, light could not travel freely. Photons were constantly scattered, trapped in a fog of charged particles. The universe was bright, but you could not see through it. Then, the universe expanded and cooled. Eventually, electrons and protons combined into neutral atoms. When that happened, the fog cleared. Light was finally allowed to travel in straight lines. The first moment the universe became transparent is what we see today as the cosmic microwave background. It is like a surface, a shell around us, not because it is a physical wall, but because it is the limit of transparency. When you look farther than that, you are looking into a time when the universe was opaque. Beyond that point, there is no ordinary light to carry information to your eyes. So the cosmic microwave background becomes a kind of visual edge, the last screen of the universe. But even that is not the ultimate boundary, because physics has other messengers besides light. Neutrinos can pass through matter more easily than photons. Gravitational waves can pass through the early universe in ways light cannot. In principle, those messengers could carry information from earlier times, from before the cosmic microwave background. That means the universe has layers of edges, like nested shells, each defined by a different kind of signal and a different kind of transparency. And this is where the story turns from distance into geometry. When people say, edge of the universe, they often mean a place you could reach, a wall, a border, a cliff. But general relativity does not require the universe to have that kind of edge at all. Space can be finite without having a boundary. It can wrap around itself. A simple analogy is the surface of a sphere. If you live on the surface, you can travel forever without hitting an edge, but the surface is still finite. It has a total area. It is limited, yet unbounded. The universe could be like that, but in 3 dimensions, not 2. That would mean the universe has a total volume, but no border where space ends, no wall, no outside. It could also be infinite. It could extend forever with no wraparound and no boundary, with the observable universe being a tiny bubble inside something far larger. Right now, measurements suggest that on the largest scales we can test, the universe is very close to flat. Flat does not automatically mean infinite, but it makes an infinite universe a simple possibility. It also means that if the universe is finite, it is so large that any curvature is too gentle for our instruments to detect easily. So when you ask for the end of the universe, you have to decide which end you mean. Do you mean the edge of what we can observe, set by the age of the universe and the speed of light? Do you mean the edge of what will ever reach us, set by acceleration and dark energy? Do you mean the last wall of light, the cosmic microwave background? Or do you mean the true global shape of space itself, finite or infinite, wrapped or open? The uncomfortable truth is that our best tools do not let us jump outside the observable bubble to check. We are trying to reconstruct the whole from a part. We are trying to infer the architecture of everything from a sky that is limited by horizons, and that is why the idea of an endpoint becomes so fascinating. Because the universe may not end like a road ends. It may end like information ends. It may end like visibility ends, or it may not end at all, except in the sense that our access to it is fundamentally bounded. In the next part, the story gets even stranger, because there is a region that is not just far away. It is causally disconnected in a deeper sense, and it might have been created by the earliest growth spurt the universe ever had. There is one more reason the universe feels like it has an edge, and it has nothing to do with a wall in space. It has to do with the way the universe began, and the fact that the beginning may have been far more extreme than most people imagine. In the earliest fraction of a second, the universe appears to have gone through a phase called inflation. The simplest way to picture it is this. Space did not just expand. Space expanded insanely fast, fast enough that 2 points could be carried apart faster than light could travel between them, not because anything broke the speed limit, but because the space in between was being created faster than light could cross it. Inflation matters for one brutal reason. It means the observable universe is not a natural boundary of the whole universe. It is just the part of the whole that got pulled into our causal reach after inflation ended locally. Our entire sky could be one small patch of a much larger reality, like a single tile in a floor that extends beyond the horizon in every direction. And this is where the idea of an endpoint turns into something almost unfair, Because if inflation happened the way many models suggest, there may not be a single edge to the universe at all. There may be endless space beyond our horizon, full of regions we will never see, not because they are hidden behind something, but because they are separated by the geometry of space-time and the timing of cosmic history. Imagine two observers in different parts of a much larger universe. Each one sees an observable bubble around them. Each one thinks their bubble is the universe they can know. Both are correct in a practical sense, and both might be living inside a reality that is vastly larger than either bubble, with no signpost telling you where the true border is, or even if a border exists. This is also where the word multiverse starts showing up in serious conversations, and it is important to keep it disciplined. The multiverse is not a sci-fi highway full of portals. In physics, it is usually a consequence of inflation models that do not end everywhere at once. In some versions, inflation stops in one region and creates a universe like ours, while other regions keep inflating. That process can, in principle, continue, producing many bubble regions that are causally isolated from each other. If that picture is real, then asking for the end of the universe is like asking for the end of a process that keeps making new space. There is no final edge you could reach. There is only the edge of what you can ever be connected to. And the weirdest part is that even inside our own observable universe, inflation leaves a faint fingerprint. The cosmic microwave background is not perfectly smooth. It has tiny variations in temperature, tiny ripples in density, the seeds that later grew into galaxies and clusters. Those seeds look random, but not too random. They look like the kind of pattern you would expect if quantum fluctuations were stretched to cosmic scales during inflation. That does not prove every inflation story, but it is one of the strongest reasons scientists take inflation seriously. It explains why the universe looks so similar in all directions and why the large-scale geometry looks so close to flat. Now put all of that together and the word endpoint starts to split into two different meanings. There is the physical shape of space. Is it infinite? Is it finite but unbounded? Does it wrap around in a three-dimensional way that no one can visualize without pain? That's a question about topology, about the global layout of the universe. And then there's the causal shape of space. What can ever affect what? What can ever exchange information? What can ever be seen, measured, or reached? That is a question about horizons. Inflation makes the causal story more dramatic because it suggests there were regions of the early universe that were pushed out of contact so fast they never had a chance to share information. It is possible that far beyond our horizon, the universe still looks broadly similar. It is also possible that it does not. Some theories allow the same underlying laws but different local outcomes, different patterns of structure, different histories. A few speculative ideas even allow different effective constants in different domains, not because the laws are chaotic, but because the deeper theory may have multiple stable ways to settle. This is the part that usually makes people feel two opposite emotions at once. One is excitement, because it hints that reality is bigger than any single sky. The other is frustration, because it hints that some parts of reality may be forever outside reach, not because we are too dumb or too early, but because the universe has built-in limits that no technology can bypass without breaking the rules that make physics coherent in the first place. So the end of the universe might not be a place, it might be a principle, a hard line drawn by causality, a boundary defined by what information can ever travel to you. And once you accept that, the most haunting possibility appears. The universe could be endless and still be lonely, not in the emotional sense, but in the physical sense. Endless space can exist, and yet each observer can be trapped inside their own causal island, with the rest of the cosmic ocean permanently out of contact. That sounds abstract until you connect it to something happening right now, something that is not a theory from the first second, but a measurement from modern astronomy. The universe is not just expanding, the expansion is accelerating, and acceleration does something to horizons that makes the idea of an endpoint feel suddenly real in a way you can almost taste. Acceleration is the quiet engine that turns infinite into unreachable. For most of human history, it felt natural to assume that if you waited long enough, you would eventually see more and more of the universe as light from farther galaxies finally arrived and the cosmic map slowly filled in. But an accelerating universe does something colder. It creates a future boundary, not a wall you collide with, but a limit that becomes more absolute with time. When expansion accelerates, there are regions of space that are not merely far away. They are being carried away from us faster and faster, so fast that their light will never catch up to our future. This is not poetry. It is a consequence of how space-time works. A galaxy can still be shining, stars can still be forming, civilizations could be rising and falling, and yet if that galaxy lies beyond a certain distance, the light it emits tomorrow will never reach us, not in 1 trillion years, not ever. Photons travel at the fastest speed nature allows, and still lose the race against the creation of new space between us. That boundary is called a cosmic event horizon. It is the universe's version of you can look, but you cannot follow. There is another horizon you already know, even if you have never used the word. The observable universe is limited because the universe has an age. Light has only had about 13.8 billion years to travel since the hot beginning, so there is a radius beyond which light simply has not had time to arrive. That is a past horizon, a limit set by finite time. The event horizon is different. It is a future horizon, a limit set by the future behavior of expansion. And if acceleration continues the way current measurements suggest, it leads to something almost tragic in slow motion. Over incredibly long spans, galaxies that are visible today will cross that line. Their light will redshift, stretch to longer and longer wavelengths, dimmer and dimmer, until it becomes undetectable. They do not vanish from existence. They fade out of our reachable sky because the space between us becomes too wide, too fast. In that far future, an observer inside a galaxy like the Milky Way would see a different cosmos. They might see only their local group, the gravitationally bound cluster of galaxies that will merge into one larger island over time. Everything else would have slipped beyond the event horizon. The night sky would still have stars, but the great cosmic web would no longer be visible. The evidence for the Big Bang would be harder to detect. The universe would look smaller, quieter, more isolated, even if the true universe outside remains vast. So when people ask, does the universe have an end? Acceleration gives a brutal answer. Even if space goes on forever, your access to it does not. The end is not a place. The end is the edge of what can ever matter to you, because matter is defined by information. If information cannot reach you, it is not part of your physical world in any practical sense. This is where the paradox bites. The universe can be infinite, and yet each observer can live inside a finite causal bubble. The universe can be full, and yet your future can become emptier. The universe can keep expanding, and yet your reachable universe can shrink. And here is the twist that makes the endpoint idea even more intense. If you go far enough into the future, the universe does not only hide places from you, it makes time itself harder to read. As expansion accelerates and light stretches, signals from deep space become slower, weaker, and more spread out. The message does not stop existing, it becomes unreadable. This is why dark energy matters so much. Dark energy is the name we give to whatever drives accelerated expansion. We can measure its effects with impressive precision, but we still do not fully know what it is. The shape of the end depends on a mystery. If dark energy stays constant, the event horizon remains and the universe drifts toward a cold future where distant galaxies slip away forever. If dark energy changes over time, the ending could be different because acceleration could weaken, could strengthen, could even reverse in some models. So at this point, the question becomes sharper, not where is the edge of the universe, but what kind of ending does dark energy write? Because the most dramatic endpoints are not about space at all. They are about fate. Dark energy sounds like a substance you could scoop into a jar, but what we actually observe is simpler and stranger. We observe a behavior. The expansion of the universe is speeding up. Not because galaxies are firing rockets, but because the space between galaxies is growing in a way that adds speed over time. If you want the cleanest mental image, think of distance itself as something that can change its rate of change. That is what acceleration means here. The first big shock came when astronomers used Type Ia supernovae as distance markers. These explosions are useful because they can be standardized well enough to act like cosmic mileposts. When teams mapped how bright they appeared at different redshifts, the pattern did not match a universe that was slowing down under gravity. It matched a universe that had started to speed up. The result was not accepted because it was dramatic. It was accepted because the alternative explanations kept failing. Dust did not fit. Simple evolution of supernova properties did not fit cleanly. The acceleration interpretation kept surviving. Then other lines of evidence joined in, and that is when it stopped being a weird result and became the default model. The cosmic microwave background, the leftover light from the early universe, tells us the overall geometry and the energy budget. Large-scale galaxy clustering and the subtle imprint called baryon acoustic oscillations act like another cosmic ruler, mapping how expansion changed over time. When you combine these measurements, you get a consistent story. Most of the universe is not made of normal matter, and the component driving late-time behavior acts like a smooth pressure that does not clump the way matter does. Here is the part that makes the endpoint question feel sharp. Dark energy is not just another ingredient. It controls the long-term future. If it behaves like a cosmological constant, meaning its density stays roughly constant as space expands, then acceleration continues and the event horizon remains. The universe does not end in a crash. It ends in separation. More and more of the cosmos becomes causally unreachable. Galaxies outside our local gravitational neighborhood fade away, not because they die, but because their light gets stretched into wavelengths so long and so sparse that no detector can realistically collect it. The sky becomes locally beautiful and globally empty. But if dark energy is not constant, the ending changes. Physics does not forbid that it could be something dynamic, like a field slowly evolving with time. If it weakens, acceleration could slow, and the future horizon could soften. If it strengthens, the horizon tightens and the future becomes more extreme. There is even a class of models where the effective pressure becomes so strong that expansion accelerates without bound. In that case, the universe does not just pull galaxies away from each other. It starts pulling apart the structures inside galaxies, then solar systems, then planets, then atoms, as if space-time itself is tearing the script. That scenario is often nicknamed the Big Rip. It is not the mainstream expectation, but it is a useful warning sign of what is mathematically allowed if dark energy is allowed to behave badly. So the real drama is not that the universe might have an edge. The drama is that the universe might have multiple endings depending on the true nature of the thing we still do not understand. The most honest statement modern cosmology can make is this: the fate of everything depends on a parameter, a behavior, a rule that we can measure indirectly but do not yet fully explain. We have the symptom. We are still hunting the cause. And this is why telescopes and surveys matter in a way that feels almost philosophical. Every improvement in measuring expansion history is not just a technical upgrade. It is a vote cast on the future. It tells us whether dark energy is steady, drifting, or something even stranger. Because once you accept acceleration, the end of the universe stops being a question about where you would go to find the edge. It becomes a question about what reality will allow you to keep in contact with, and for how long. When people say, the edge of the universe, they usually imagine a place you could travel to, a final wall where reality stops and something else begins. But the most unsettling thing cosmology teaches is that the edge is not a place. It is a limit in information. It is the boundary of what can ever reach you, no matter how long you wait, no matter how powerful your telescope becomes, no matter how fast you try to move. Light has a speed limit, and the universe has an age. Those two facts alone create a horizon. The observable universe is not the whole universe. It is the region whose light has had time to arrive since the beginning. Beyond that, there can be galaxies, structures, even entire superclusters, and they could be as real as anything you have ever seen. But their light has not reached us yet, not because something blocks it, but because the clock has not run long enough. Here is the weird part that makes the word edge feel tempting. The boundary of the observable universe is not a wall. It is a sphere around us made of time. When we look far away, we look back in time. Farther means earlier. Push far enough and you are not seeing galaxies at all, because galaxies did not exist yet. You see the universe when it was hot, dense, and young. Push even farther and you hit a fog, a moment when the universe was so ionized that light could not travel freely. The first clear light we can see comes from when the universe cooled enough for atoms to form and photons to stop scattering constantly. That light is still here, stretched into microwaves, filling the sky from every direction. It is not just a pretty relic, it is a hard ceiling for ordinary vision. It is the oldest picture we can take, because earlier than that the universe was opaque. So if there is an edge, why does it feel like a horizon instead of a curtain you can open? Because even beyond the oldest light, there are limits built into space-time itself. The particle horizon is the boundary of what we can see today. But the event horizon is the boundary of what we will ever be able to see, even in the infinite future. This is where dark energy becomes more than a technical detail. If the expansion keeps accelerating, there are regions of space that are not merely far away. They are running away in a way that prevents their future, light, from ever reaching us. Not because it cannot move fast enough, but because the space it travels through keeps growing faster than the light can make progress across the distance. That is the most honest version of the edge. It is not the end of space. It is the end of causal connection. There are parts of the universe that are already, right now, permanently outside our future. They exist in the same reality, governed by the same laws, but they are separated by the geometry of expansion, like two ships drifting apart on an ocean that is itself expanding between them. No engine can close the gap if the ocean grows too fast. And there's another twist that makes this feel personal. The horizon depends on where you are. Every observer in the universe has their own observable sphere centered on themselves. There is no universal spotlight that reveals the same boundary to everyone. The edge is not a feature out there. It is a feature of your position and your time. It is the map drawn by your past light cone, the set of events that can influence you. Change the observer, you shift the sphere. The universe does not have one edge. It has countless horizons stitched together by the speed of light and the age of time. This is why the phrase, "the universe is expanding," can sound gentle and still hide something brutal. Expansion is not just galaxies moving apart. It is the universe rewriting what can ever be known. The longer acceleration continues, the more the cosmos edits itself into isolation. In the far future, distant galaxies will fade, not because they stop shining, but because their light will be stretched into wavelengths so long and so thin that it becomes effectively undetectable. The sky will still have stars, but the grand cosmic web will vanish from view. An advanced civilization born too late could look up and see only their local island of galaxies and conclude that the universe is small, static, and empty. They would be wrong, and they might never have enough information to prove it. So when you ask where the universe ends, the deeper question is what the universe allows you to be connected to. The end is the line where signals stop arriving, where the story stops updating, where the outside becomes permanent silence. Not silence because nothing is happening, but silence because space-time has made distance into a one-way door. And that raises the next terrifying, beautiful idea. If the observable universe is a bubble of reachable information, and if the bubble is not the whole, then the universe could be vastly larger than our cosmic map, maybe even infinite. Which means the phrase, "everything that exists," might be bigger than any picture, bigger than any survey, bigger than any future archive of data. The edge is not a wall you hit. It is a horizon you carry with you, a boundary written into the physics of light, time, and expansion. If horizons are the first kind of end, then the second kind is colder and stranger. It is not an edge in distance, it is an edge in meaning. It is what happens when the universe keeps expanding, keeps thinning out, and keeps pushing everything toward a future where structure becomes harder to maintain. This is where the end of the universe stops sounding like a place and starts sounding like a fate. Right now the universe looks busy. Galaxies glitter, stars burn, black holes feed, new stars still form in gas clouds, chemistry is active, planets cool, life, at least here, makes noise. But that activity depends on gradients, differences in temperature, differences in pressure, differences in density. Life itself is an expert at exploiting differences. A cell is a machine that lives on imbalance. A star is a furnace that exists because its core is hotter than the space around it. A galaxy is a pattern that exists because gravity can still gather matter into clumps. If the universe ever loses its gradients, it does not explode. It simply stops doing interesting work. That is the idea behind the heat death of the universe. It is not a dramatic death, it is a slow smoothing. Over time, stars burn through their fuel. Star formation slows because galaxies run out of cold gas. The bright blue era ends. The galaxy becomes older, redder, quieter. White dwarfs cool. Neutron stars cool. Black holes become the last major engines not because they create light, but because they store mass and can convert it into radiation when they feed or merge. Even then, black holes are not eternal in the deepest physics. If Hawking radiation is real in the way we think, black holes will eventually evaporate, leaking their mass away extremely slowly, taking absurd lengths of time. The universe does not collapse into nothing. It dissolves into thin, cold particles and long wavelengths of radiation spread across an expanding space. The scary part is not that everything ends. The scary part is that the universe keeps going without anything left to do. A future where there are no new stars is a future where the sky is dark in a very different way than it is now. It is not a poetic darkness full of potential. It is a functional darkness where the main light sources are gone and the remaining matter is sparse, separated, and cold. It is a universe still obeying laws, still expanding, still full of space, but with almost no energy left that can be harvested to build complexity. This is why, when people ask for the edge, physics sometimes answers with time instead of distance. The end may not be a boundary you travel toward. It may be a direction the universe is already moving in. The cosmic clock is not counting down to a bang. It is counting down to stillness. But even here, the universe has more than one way to end, and the difference depends on one thing we still do not fully understand: dark energy. If dark energy is truly constant, like a cosmological constant, then the heat death picture is the likely long story. Eternal acceleration, galaxies slipping beyond horizons, local gravitational islands remaining, then eventual fading into cold, dilute emptiness. But if dark energy evolves, if it changes with time, then the universe can become weirder. There is a scenario called the Big Rip, where the acceleration grows stronger over time. Not just faster expansion, but expansion that eventually overwhelms every binding force. First, galaxy clusters fall apart, then galaxies, then solar systems, then planets, then atoms. In that future, the universe does not quietly fade. It tears. The fabric stretches so aggressively that even the forces holding matter together cannot compete. It is an edge not in space, not in temperature, but in the integrity of structure itself. And there is another scenario, almost the opposite, called the Big Crunch. If the expansion slows and reverses, if gravity wins back the long game, the universe could collapse into a hot, dense state again. That ending is dramatic, but it is not currently the favored direction from modern measurements. The point is not which ending is correct. The point is that the end is not a single idea. It is a family of fates, and the one we get depends on how the energy content of the universe behaves as time stretches forward. This is where the phrase, "the end of the universe," becomes a scientific question, not a poetic one. Because the universe's fate is encoded in the way expansion changes over time. Measure the expansion history well enough, and you narrow the list of endings. You turn the apocalypse into an equation with error bars. That is the strange comfort of physics. It does not promise good news. It promises clarity. And clarity leads to one more unsettling thought. If the observable horizon is shrinking in practical terms because of acceleration, then the universe is not only evolving physically, it is also evolving epistemologically. The amount that can ever be known may decrease for future observers. The universe can become harder to read. In that sense, the end is also an end of evidence, an end of data, an end of the ability to reconstruct cosmic history, because the signals we rely on disappear beyond horizons or fade below detection. So, the edge of the universe has two faces. One is spatial, a horizon that limits what can reach us. The other is temporal, a future that limits what can keep happening. In both cases, the universe does not slam into a wall. It glides toward a limit, and the limit is written into the geometry of space-time and the accounting of energy. And now the next step is unavoidable. If the universe has horizons, and if its long future might be a slow isolation, then the question becomes sharper and more personal. Are we looking at the universe as it is, or are we looking at the only slice we can ever access, while something larger continues beyond every boundary we can define? There's another trap hidden inside the phrase, "the edge of the universe." It makes you picture a wall, a border, a hard line where space stops and something else begins. But physics has never liked walls unless it absolutely has to. When the universe looks like it has an edge, it is usually because the observer has an edge. Start with the simplest possibility. The universe might be infinite, not just very big, but truly without end. If you travel forever in any direction, you never reach a boundary because there is no boundary to reach. That sounds like science fiction, but mathematically it is one of the cleanest options. The problem is not imagining it. The problem is proving it. You cannot prove infinity by looking out from one spot, because any telescope view is finite by definition. No matter how far you see, you can always ask what is beyond what you see. Then there is the second possibility, and it is the one that breaks people's intuition in a very quiet way. The universe can be finite and still have no edge. The classic analogy is the surface of a sphere. If you walk on Earth long enough in one direction, you do not fall off an edge. You eventually come back. The surface has a limited area, but no boundary. Now take that idea and upgrade it. Do not imagine a two-dimensional surface. Imagine three-dimensional space itself having that property. A space where you can keep going and still never reach a wall because space wraps in on itself. Finite volume, no edge. The phrase for this is sometimes compact without boundary. It sounds like a trick, but it is exactly the kind of trick geometry allows. If that were true, the edge of the universe would not be a place. It would be a loop. In principle, a beam of light could travel far enough and return. In principle, you could see the back of your own galaxy from another direction, like reflections in a hall of mirrors, except the mirror is topology, not glass. That sounds wild, but it is not illegal physics. It is allowed. The universe is under no obligation to be shaped in a way that feels natural to a primate brain that evolved to throw rocks. So how do we even test this? We do not fly to the end. We look for fingerprints in the sky. The most important fingerprint is the oldest light we can observe, the cosmic microwave background, the afterglow from when the universe first became transparent. That glow is like a photosphere around us, not because it surrounds us physically, but because it is the boundary of what light can show. Before that time, the universe was a hot plasma fog that scattered photons constantly. Light could not travel freely. When atoms formed and the fog cleared, light was released, and that light has been traveling ever since. We see it today as a faint microwave glow in every direction. This is where the edge becomes almost sneaky. The cosmic microwave background looks like a wall at first. It is the farthest light we can see. It is the farthest back in time ordinary photons can show us directly. People call it the surface of last scattering, and it behaves like a horizon. But it is not the edge of space, it is the edge of visibility. It is a time barrier. It is the moment the universe stopped being opaque. The universe could continue beyond it in distance, and it absolutely continues beyond it in time. But light from earlier times is trapped behind the fog. The edge is not a border of existence, it is a border of information. If you want to know whether space is finite or infinite, you look at patterns in that ancient glow and ask whether the universe repeats itself. If space wraps around, you might expect repeating structures, matched circles, duplicated patches of the same ancient pattern appearing in different directions. People have searched for these kinds of signatures. It is hard. Noise, foreground dust, instrument limits, and the sheer complexity of the sky make it a brutal puzzle. So far, the simplest reading is that if the universe is finite, it is at least much larger than the part we can observe. It could wrap, but the loop might be too big for the cosmic microwave background to reveal clearly. Or it could be truly infinite. The universe does not owe us a decisive answer on our schedule. And then there is curvature. This is another word that sounds like shape, but it is really about geometry. Space can be flat, positively curved, or negatively curved. Flat does not mean infinite, but it often goes with the infinite picture. Positive curvature goes with sphere-like behavior and can go with finite space without an edge. Negative curvature tends to behave like a saddle and often goes with an infinite layout. Measurements so far suggest space is very close to flat on the scales we can measure. But close to flat is not the same as perfectly flat, and perfectly flat is not the same as infinite. The precision keeps improving, but the universe keeps being subtle. Now, here's the part that feels almost unfair. Even if the universe has no edge, even if it is infinite or wraps without boundary, you still face a very real end. The observable universe. That is not a guess. That is a physical fact defined by the speed of light and the age of the universe. There is a radius beyond which light has not had time to reach us since the beginning. That creates a horizon, and that horizon is an edge in the only sense that matters operationally. It is the edge of contact, the edge of evidence, the edge of causal influence. And because of cosmic acceleration, that edge becomes more dramatic. Some galaxies are already effectively beyond future contact. Their light that is reaching us now was emitted long ago. The light they emit in the far future may never reach us, because space expands in between faster than the light can close the gap. The universe is not only large, it is actively hiding itself over time. The cosmos is building a privacy curtain, not out of conspiracy, but out of geometry. So when people ask what is beyond the edge, the most honest answer is that beyond the edge is more universe, but it is a universe that cannot currently matter to us and may never matter to us, because information from there cannot arrive. It is not forbidden to exist, it is simply forbidden to be known by us, at least not by any method that obeys relativity. This is where the story starts to feel almost philosophical without needing fantasy. Because it forces a distinction that most people never make. There is the universe as a whole, whatever that means in total, and there is the universe as an observable system, the only part we can ever test directly. Those two are not guaranteed to be the same size. They are not guaranteed to have the same properties. The observable region could be one small patch inside something far larger, just as your neighborhood is not the same thing as Earth. Inflation makes this idea even sharper. In many models, inflation is an early period of rapid expansion that can make space look extremely flat and uniform within any observable patch, while still allowing the whole to be enormous, possibly vastly larger than what we can see. In that picture, our observable universe is like a bubble of clarity inside a much bigger reality. Not necessarily multiple universes in the pop culture sense, but multiple regions of space-time that are causally disconnected, meaning no signals can travel between them now or in the future. They are not separated by a wall. They are separated by the fact that light cones do not overlap. So is there an edge? The answer depends on what you mean. If you mean an edge where existence stops, physics gives no evidence for that. If you mean an edge where information stops, the universe absolutely has that, and it is sitting around us right now like a boundary we cannot cross. If you mean an edge where the future stops producing complexity, then yes, depending on the fate of expansion, the universe may have an end state where structure becomes impossible to maintain. And if you mean the edge of what can ever be proven, then the edge might not be a distance at all. It might be a limit built into the relationship between observation and reality. This is why the end of the universe is such a powerful idea for an audience. It sounds like a place. It turns out to be a set of limits. Limits of sight, limits of time, limits of causality, limits of energy. The universe is not trying to scare you with a cliff. It is doing something more unsettling. It is showing you that reality can be bigger than knowledge and that the gap between them is not a failure of technology. It is a feature of space-time itself. And that sets up the next question, the one that always arrives after you accept horizons. If we cannot reach the edge, can we still map it? Can we still infer what the whole is like from the small piece we are allowed to see? Because that is what science does when the universe refuses to fit inside a human frame. It builds models that reach beyond direct vision, then asks reality to confirm them through fingerprints, patterns, and constraints. Once you accept that the edge is really a horizon, the next step is almost inevitable. You start asking what kind of universe produces horizons like ours, and what kind of universe makes horizons permanent. Because there is a big difference between we cannot see it yet and we will never see it, no matter how long we wait. In the early universe, horizons were simple. The universe was younger than the light travel time across huge distances, so of course there were regions that could not have exchanged information yet. That is normal. But then cosmology noticed something disturbing. The cosmic microwave background is extremely uniform in temperature across the sky, even in regions that should never have been in causal contact in the standard expansion picture. How did those regions coordinate? How did the universe become so smooth on large scales if different parts could not talk to each other early on? Inflation was introduced to solve that, not as a vibe, not as poetry, but as a mechanism. A very brief era where space expanded insanely fast, stretching a tiny, already connected patch into something large enough to contain our entire observable universe. In that story, the smoothness is not mysterious. Everything was close together before inflation, so it could equilibrate. Then inflation blew it up like a snapshot being zoomed until the pixels become the sky itself. The weird part is what inflation implies if you take it seriously. If inflation happened, it may not have happened only once, and it may not have ended everywhere at the same time. In many versions of the theory, inflation is not like a firework that explodes and stops. It is like a process that continues in some regions while ending in others. Where it ends, you get a hot big bang-like region, a bubble of normal expanding universe. Where it continues, space keeps inflating, creating more room for more bubbles to form. This is called eternal inflation, and it is one of the cleanest ways physics produces something multiverse-like without trying to be dramatic about it. Now, the word multiverse instantly drags in portals, mirror worlds, and sci-fi noise. That is not what this is. In this framework, other universes are basically other regions of space-time that are causally disconnected from ours. Not separated by a wall, but separated by the structure of expansion. If light can never travel from there to here, then from our perspective, they are unreachable in principle. They can exist and still be forever outside our evidence cone. That sounds like a convenient story because it can hide anything beyond the horizon. That is why it is controversial. Science hates ideas that cannot be tested. So the real question is not, is a multiverse cool? The real question is, does the multiverse leave fingerprints in the only sky we have? There are a few ways it might. One possibility is bubble collisions. If our region formed as a bubble in a larger inflating background, another bubble could have formed nearby and collided with ours early on. That collision could leave a subtle scar in the cosmic microwave background, like a circular or disk-like anomaly, a faint pattern that does not match random fluctuations. People have searched for these signatures. The results so far are not a slam dunk. There are interesting features, but nothing that forces the conclusion. The sky is messy, statistics are cruel, and humans are good at seeing faces in noise. Another possibility is that inflation predicts a particular pattern of fluctuations, a specific distribution of ripples in the early universe that later became galaxies. The power spectrum, the tilt, the degree of non-randomness, the way fluctuations correlate at different scales, these are places where models can be tested. Inflation has done well in broad strokes, but it is not one theory. It is a family of theories, and different versions make different predictions. Some are already disfavored, some are still plausible. The data keeps narrowing the zoo. Then there's the quietest clue of all. Dark energy. The thing accelerating cosmic expansion today. We do not fully understand what it is. It could be a cosmological constant, a fixed energy density of space. It could be a dynamic field that changes over time. It could be something even stranger. But its existence means the observable horizon is not just a temporary inconvenience. It becomes a permanent feature of the future. The universe can become more isolated with time, not less. If dark energy remains roughly constant, then as billions and trillions of years pass, distant galaxies will slip beyond our horizon one by one. Their light will redshift until it is too stretched to detect, and then it will stop reaching us at all. Eventually, local group galaxies that are gravitationally bound to us will remain, but everything else will fade. From that far future viewpoint, the observable universe will look smaller, emptier, and more lonely. Not because reality shrank, but because information got cut off. Here is the brutal twist. A civilization living far in the future might not even be able to discover the Big Bang using observation alone, because the cosmic microwave background will be stretched to wavelengths so long it becomes undetectable, and the evidence of expansion will be hidden beyond the horizon. They could live inside a universe with a rich past, and yet their sky would not show it. They would be trapped in a cosmic island with no memory in the light. That is not philosophy. That is a consequence of expansion plus horizons, and it changes what it means to ask about the end of the universe. The end might not be an explosion or a collapse. The end might be informational. The universe keeps existing, but it becomes observationally smaller, quieter, harder to reconstruct. Reality continues while knowledge becomes local. This is why the edge of the universe is such a psychological hook, because it turns the idea of beyond into a practical limit. There may be more galaxies than we can ever count. There may be more space than we can ever map. There may even be other bubble regions with different histories. But the cosmic speed limit and accelerated expansion create a hard boundary around what any observer can ever access. And once you see that, you start realizing the most haunting version of the end is not the end of things. It is the end of access, the end of signals, the end of outside information. A universe that is still enormous, but that slowly closes the curtains on everything beyond the local stage. That sets up the next part perfectly, because if horizons define the edge, then the real drama becomes time. Not time as a clock on the wall, but cosmic time as a one-way process that changes what can exist, what can form, what can survive. When people say the end of the universe, what they really mean is what happens when time runs long enough that the universe runs out of ways to stay interesting. Cosmic time is not just a longer version of human time. It behaves like a slow machine that changes the rules of what can happen. Right now, the universe is in a rare, bright phase where stars are common, galaxies are full of light, and chemistry has enough energy to stay interesting. But that phase is not permanent. It is a temporary window, and the unsettling part is that we can already see the window starting to close. Star formation peaked billions of years ago. The universe used to make stars faster than it does today. That means we are living after the cosmic high point in the long come-down, where the raw fuel for new stars is being slowly used up or locked away. Gas turns into stars, stars burn that gas into heavier elements, and over time the easy-to-use hydrogen gets harder to access. Galaxies do not run out of matter. They run out of free cold gas that can collapse into new suns. Gravity keeps trying to build. The universe keeps expanding and thinning things out. It is a tug of war, and expansion has a lot of patience. If you zoom forward far enough, the sky changes character. The bright, massive stars die first because they burn fast. The galaxies gradually become dominated by smaller, longer-lived stars. Red dwarfs become the main light sources. These stars are small, cool, and unbelievably long-lasting. They can burn for trillions of years. That number is so large it breaks normal intuition. It means the era of starlight is not ending soon, but it is ending eventually, and the kind of light we get becomes dimmer and redder as time goes on. Then, the universe starts to look like an old city at 3 in the morning. Fewer lights. Longer silence between events. Stellar nurseries fade because the gas is either consumed or scattered. Star formation slows down toward zero, not with a bang, but with a quiet exhaustion. Galaxies still exist, but they become museums of aging objects. White dwarfs, the leftover cores of sun-like stars, pile up. Neutron stars and black holes accumulate. Most of the mass ends up in things that do not shine. In that far future, the most common objects are dead stars, not living ones. White dwarfs cool slowly, fading toward darkness. Neutron stars lose heat. Even the last red dwarfs eventually run out of fuel. When that happens, the universe enters a phase where there are no new sources of starlight being created, and the existing ones are all dying out. The night sky becomes almost completely black, not because space is empty, but because the engines that make light are gone. At that point, the universe is still full of matter, but it is starving for usable energy. This matters because complexity is not only about having stuff. Complexity is about having gradients, differences, flows. Life, weather, chemistry, and even galaxies depend on energy moving from high to low, from hot to cold, from concentrated to spread out. When everything becomes evenly cold and evenly thin, there is no more free lunch. You cannot build new structures if there is no energy difference left to power the building. This is the core idea behind heat death. It sounds dramatic, but it is actually the least dramatic ending. In the heat death picture, the universe does not explode. It does not collapse. It just approaches a state of maximum entropy, a fancy way of saying maximum sameness. Everything spreads out, everything cools down. Fewer and fewer events happen because there are fewer and fewer energy differences to drive them. The universe becomes a quiet, almost frozen equilibrium. And yet, even in that deep future, one kind of object still dominates the story. Black holes. They are the ultimate long-term storage units. They can outlive stars. They can outlive galaxies in any meaningful sense. In a universe where almost everything fades, black holes remain as the last major structures, heavy and silent, holding enormous mass behind horizons. But even black holes are not eternal, at least according to our best current physics. Quantum theory combined with relativity suggests they can slowly lose mass through Hawking radiation, an incredibly faint effect where black holes leak energy over absurd timescales. The bigger the black hole, the slower the leak. For the largest ones, the timescales are so enormous that writing the number is basically a performance art piece, but the idea is simple. Even the darkest objects are not perfectly stable. Given enough time, they evaporate. So the heat death story ends in a strange way. After the last stars fade, after the last black holes leak away, what remains is a universe filled with thin radiation, scattered particles, and an ocean of cold emptiness expanding forever. Not nothing, but almost nothing. A universe that still exists, but has lost the ability to make new, complex things in any normal way. That is the slow ending, the quiet ending. The one that feels like a cosmic fade-out instead of a finale. But the universe is under no obligation to choose the quiet ending. Because there are other possibilities that are more sudden, more violent, and more unsettling. Endings where the rules themselves change. endings where the fabric of reality does not simply cool down, but snaps into a different state. And if that can happen, then the edge of the universe is not only a horizon in space, it is a horizon in stability. That is where the story gets sharp, because the next endings are not about running out of fuel. They are about the universe changing the game mid-play. There is a version of the future where the universe does not fade out. It breaks. Not like glass shattering in a loud room, but like a rule quietly flipping when nobody is watching. Everything still looks normal right up until it is not. Stars still burn, galaxies still spin, your physics textbook still works. And then one day, the universe discovers that the state it is living in was never truly stable. It was only pretending. To understand this, you have to think about emptiness in a different way. In everyday life, empty space sounds like nothing. In modern physics, empty space is not nothing. It is a state, a vacuum state, and like any state, it can have different energy levels. The disturbing idea is that our universe might be sitting in a vacuum that is not the lowest possible one, not the true ground floor. More like a high shelf that feels stable because it has been stable for a very long time. If that is true, then the universe is living in a false vacuum, a metastable state, stable enough to last billions of years, but not guaranteed forever. It is like a ball resting in a shallow dent on a hillside. It can sit there for a long time. But the laws of quantum mechanics allow tunneling, meaning the ball does not need a push to escape. It can, in a sense, simply appear on the other side of the hill because reality permits rare jumps that ignore the usual barriers. If a false vacuum decay happens, it does not happen everywhere at once. It begins as a bubble, a tiny region where the vacuum flips into a lower energy state. Inside that bubble, the laws of physics may not be the same. The strengths of forces could shift. Particle masses could change. Chemistry as we know it could stop working. Atoms might not hold together the same way. The periodic table might become meaningless. You do not get a warning. You do not see it coming on a telescope, because the bubble expands at essentially the speed of light. By the time the information reaches you, the bubble is already here. That is the part that people fixate on, the cinematic doom. But the deeper point is, we are talking about the universe having more than one set of possible rules, and we happen to live under the version that allows stars, life, and long stories. A vacuum decay would be the universe switching to a different version, not because it hates us, but because physics is allowed to settle into a more stable configuration. Now, is this likely? Nobody can honestly claim they know. We can make calculations based on what we know about fields like the Higgs field, and some results suggest our vacuum might be metastable rather than absolutely stable. But there are uncertainties. The exact values of fundamental parameters matter, the unknowns matter, the model assumptions matter. The universe does not sign a contract explaining its long-term plans. Still, the concept matters, because it changes how you think about the edge or the end. It says the most important boundary might not be a wall in space, it might be a boundary in the state of reality itself. And if vacuum decay sounds too abstract, there is another brutal ending that does not require new physics at all. It only requires one thing: dark energy staying exactly as it is or getting stronger. Right now, the expansion of the universe is accelerating. That means distant galaxies are not just moving away. The rate at which the distance grows is increasing. Over very long times, this creates a practical horizon, a limit to what can ever be reached or even contacted. Light from far regions can become unable to reach us because the space in between stretches too fast. The universe does not need a physical wall to create an unreachable edge. Acceleration creates an edge automatically. In the mild version, this just makes the universe lonelier in a cosmic sense. Distant galaxies fade out of view, not because they disappear, but because their light gets stretched, diluted, redshifted into darkness. Over time, observers in a far future galaxy would see fewer and fewer other galaxies. Eventually, they might see only their local group and nothing beyond. The universe would look smaller, even while it becomes larger, a cosmic illusion caused by expansion. But there is a harsher version. If dark energy is not perfectly constant, if it grows with time, The acceleration can become so strong that it starts tearing apart structure. First, galaxy clusters lose their grip, then galaxies, then solar systems, then planets, then atoms. This is the Big Rip scenario. It is basically the universe saying, no more binding, no more togetherness. Everything gets pulled apart because the stretching of space overwhelms every force that tries to hold matter in one piece. Again, we do not know if that is what will happen. Observations so far are consistent with dark energy behaving like a constant, like a steady pressure baked into space itself. That points more toward the quiet loneliness scenario than the ripping one. But the uncertainty is not zero. And the concept is too important to ignore because it turns the end of the universe into a question about one number, the equation of state of dark energy. If it is exactly -1, you get a slow drift into isolation. If it is less than -1, you get the rip. A tiny difference in a parameter and the fate of everything changes. So now the story has two kinds of edges. One is an edge of emptiness, the heat-death fade out where the universe runs out of useful energy. The other is an edge of rules, where the vacuum could change or the expansion could become violently dominant. And both of them share the same eerie theme. The universe does not have to end with an explosion to be terrifying. It can end by becoming too smooth to care, or it can end by changing its rules so completely that the word care no longer applies. But there is one more kind of edge that is even stranger than endings, because it is not at the end of time. It is an edge we live inside right now. It is the edge of what we can ever observe, even if the universe lasts forever. If you want the creepiest part of cosmology, it is not the monsters. It is the limits. Because there is a boundary around you right now, at this moment, and it is not a wall you could fly toward. It is not a cliff at the edge of space. It is a horizon made of time, expansion, and the simple fact that light has a speed limit. And once you really get that, the end of the universe stops being a place. It becomes a condition. The observable universe is not the whole universe. It is only the part whose light has had enough time to reach us since the beginning. That sounds obvious, but it is a deep trap for human intuition. We naturally assume the universe is what we can see if we just build better telescopes. But some regions are not hidden by dust or distance in the ordinary sense. They are hidden by history. The light has not arrived yet, and in an accelerating universe, some light never will. That is the first horizon, the particle horizon. It marks the farthest distance from which light could have reached us since the early universe became transparent. It is the boundary of our cosmic past. Beyond it, there may be galaxies, structures, or entire regions of spacetime that are real but unobservable to us, not because we are weak, but because causality is strict. Then there is the second horizon, the event horizon of cosmic acceleration. This one is colder. It is the boundary of our cosmic future. It separates regions whose light will never reach us no matter how long we wait, because space between us is expanding too fast. This is not science fiction. This is a direct consequence of accelerated expansion. If that acceleration continues, the universe will gradually turn into islands of matter separated by a sea of space that effectively becomes untouchable. That means there is a kind of end already built into the structure of reality. Not an end of existence, but an end of connection. There are places where events can happen, and we will never know. Not because nobody is looking, but because physics itself refuses to deliver the information. Now, connect that to the idea of a multiverse, and things get weirder without needing any magic. In inflationary cosmology, the early universe may have expanded at an almost absurd rate. Inflation is not just expansion. It is expansion so fast that tiny quantum fluctuations got stretched into cosmic scales, becoming the seeds of galaxies and the large-scale structure we see today. Inflation is one of the best explanations for why the universe is so uniform on large scales, why it is so flat, why distant regions look strangely similar. But inflation has a wild implication. In some models, inflation does not stop everywhere at once. It ends in patches, bubbles. local regions where inflation ends and a hot Big Bang-like phase begins, while other regions keep inflating. If that happens, then what we call our universe might be one bubble among many, each separated by vast inflating space that prevents contact. Not parallel worlds in a fantasy sense, just causally disconnected regions of space-time produced by the same process. In that picture, the end of the universe is not a single ending, it is a landscape. Different regions can have different histories, different horizons, possibly different low-energy physics depending on how fields settle. If you hear people say many universes, this is one of the serious ways it can mean something scientific, not a portal story, but a consequence of inflation combined with causality. But the story gets sharper when you add the idea of vacuum states. If the vacuum can exist in multiple energy levels, then different regions of the larger spacetime could sit in different vacuum states. Some would have physics like ours, some could be sterile. Some could have no stable atoms, some could inflate forever, some could collapse quickly. The multiverse, in this disciplined sense, is not a party of infinite copies. It is a set of outcomes in a bigger structure where different pockets settle into different rules. This is why the edge of the universe becomes the edge of the knowable. Even if there is a huge reality outside our horizon, it might be permanently beyond verification. And that creates an uncomfortable gap between what is real and what is testable. Physics does not like untestable claims. Good physics does not fall in love with ideas just because they are big. It demands fingerprints, observable consequences. And this is the hard question. If there are other bubbles or other vacuum domains, can they leave marks on our sky? Possibly. Some models predict that if bubble universes collided in the early stages, they might leave subtle signatures in the cosmic microwave background, the afterglow radiation from the early universe. Not a clear message, not a picture, but a pattern. A faint asymmetry, a circular imprint, a statistical anomaly. People have searched. The evidence is not decisive. The universe is noisy, and human brains are great at seeing shapes that are not real. Still, this matters to our story because it frames the end and the edge as the same theme. A horizon is a boundary where information stops. Whether you talk about the end of time or the end of what can be observed, you are dealing with limits on connection, and that returns us to your video's core vibe. The cosmos is not frightening because it is full of threats. The cosmos is intimidating because it is full of distance, time, and boundaries that do not care about desire. But here is the twist. Those boundaries are not only depressing, they are also what make meaning possible. Because without causal structure, without horizons, without rules, nothing could persist. Nothing could be stable. No stars, no clocks, no life. The same limits that keep the universe from being a crowded room are the limits that keep it from being chaos. Now, there is one more end that combines everything we have talked about, and it is the one people almost never imagine correctly. It is not the end of matter. It is not the end of light. It is the end of complexity. Because the universe can keep existing for an absurd amount of time while slowly losing the ability to do anything interesting. The long fade. The quiet dying of gradients, the moment when there's no useful difference left to exploit. And, if that is true, the most terrifying edge might not be far away. It might be the day the universe becomes too uniform to tell a story. That is where we go next. The end that scares cosmologists the most is not an explosion. It is a slowdown. It is the universe running out of differences. Life, stars, weather, fire, computers, even your own thoughts, all of it depends on gradients. Hot versus cold, dense versus empty, high energy versus low energy. Whenever there's an imbalance, something can happen. Energy can flow, work can be done, stories can unfold. Entropy is the name we give to the universe's habit of smoothing those differences out, not out of cruelty, not out of intention, just out of statistics. Systems tend to move toward states that can happen in more ways. Mixed is more likely than separated. Lukewarm is more likely than half boiling and half frozen. Over long enough time, the universe does what spilled perfume does in a room. It spreads until you cannot point to a source anymore. This is why the phrase heat death is so misleading. It sounds like a dramatic moment. It is not. It is a slow fading of usefulness, a universe that still exists but cannot easily do anything new, a universe where energy is still present, but it is too evenly distributed to power complex structures. If dark energy continues to drive accelerated expansion, the distant universe becomes less and less reachable. Galaxies outside our local group slip beyond the event horizon. Their light gets stretched, redshifted, and dimmed until it becomes effectively unobservable, not because the galaxies vanish, but because the universe grows too fast for their signals to keep up. On human time scales, this feels abstract. On cosmic time scales, it becomes a rearrangement of reality. The night sky would slowly lose its depth. Far future observers would see fewer galaxies, then fewer stars, until the visible universe becomes a small island of gravitationally bound matter surrounded by darkness. A horizon does not have to be close to be real. It just has to be final. Then, the stars begin to go out, not all at once, but one category at a time. The most massive stars burn fast and die first. Sun-like stars last longer. The smallest red dwarfs can burn for trillions of years, which means the longest-lived lights in the universe are also the faintest. The universe does not end with a bang. It ends with a long series of dimming bulbs. After the era of bright star formation, you enter a universe dominated by remnants, white dwarfs cooling into black dwarfs, neutron stars slowly losing energy, planets drifting in the dark, occasional collisions, rare flares, but the average trend is towards silence. If protons are unstable, as some theories suggest, then even ordinary matter does not last forever. That would mean the atoms in everything eventually decay, extremely slowly, into lighter particles and radiation. The details are not confirmed, but the possibility shows the direction of the arrow. Even the most solid things might be temporary on deep time, and then there are black holes, the final hoarders of energy and structure. In the long future, black holes could become the last major objects left, swallowing stray matter, merging and then waiting. A black hole looks eternal, but even it may not be. If Hawking radiation is correct, black holes very slowly leak energy and evaporate. The biggest black holes take the longest, so the final era of black holes would be the universe's last slow fireworks, except the fireworks are so spread out in time that no one would call it a show. After that comes the dark era, a universe with extremely low energy particles, thin radiation, and enormous empty volumes expanding forever. Physics does not stop working. Time does not necessarily stop. But the capacity for complexity collapses. No easy gradients, no abundant fuel, no convenient temperature differences. A universe that is technically alive, yet practically quiet. That is the heat death story. It is not certain, but it is the default ending in many models because it follows from a simple idea. If the universe keeps expanding and entropy keeps rising, you drift toward a state where almost nothing happens. But cosmology has other endings on the menu, and some of them are stranger. One is the Big Rip. If dark energy grows stronger over time, expansion could eventually overcome every binding force. First galaxy clusters would come apart, then galaxies, then star systems, then planets, and in the extreme version, even molecules and atoms. This is not the mainstream expectation, but it is a reminder that the future depends on what dark energy actually is, not what we assume it is. Another is the Big Crunch, where expansion reverses and the universe collapses back into a hot, dense state. Current observations point more toward continued expansion, but the crunch remains a conceptual mirror, a warning not to treat today's trend as destiny without evidence. And then there is the most unsettling ending because it is not gradual. Vacuum decay. In quantum field theory, the vacuum is not just empty space, it is a state, the lowest energy arrangement of fields. It is possible in some scenarios that our vacuum is not the absolute lowest state. It could be metastable, like a ball sitting in a shallow dip rather than the deepest valley. It looks stable, it acts stable, but in principle it could tunnel to a lower energy state. If that happened, a bubble of a new vacuum would form and expand at nearly the speed of light. Inside that bubble, the laws of physics could be different because the underlying field configuration is different. Chemistry might not work, atoms might not exist, time and space could behave differently. This is not a monster you can see coming, because the bubble wall would arrive at light speed. There is no warning you can observe in advance. This is not a prediction that it will happen. It is a possibility that exists because quantum physics allows tunneling and because we do not fully know the stability of our vacuum. Most likely, if the vacuum is metastable at all, it lasts far longer than the current age of the universe. But even that phrase is chilling because it reveals a new kind of edge, not the edge of space, but the edge of a state. So when people ask for the end of the universe, the honest answer is that we have multiple endings depending on which part of physics wins. Slow fade, violent tear, cosmic collapse, or a sudden phase change in the ground state of reality. And now we hit the core point that makes this story feel different from ordinary science content. Every ending is really an argument about laws, about whether dark energy is constant, about whether protons decay, about whether black holes evaporate, about whether our vacuum is stable. The end is a measurement problem, because the universe will choose the ending. But we can still ask which ending the evidence supports. And to do that, we need to talk about the data we can actually touch right now. The expansion history, the cosmic microwave background, the distribution of galaxies, the way light gets stretched, the way structure forms and freezes out. The universe is not hiding the answer completely. It is just answering in slow motion. In the next part, we stop treating the end as a philosophical idea and start treating it like a detective case, where every clue is a number, every number is a measurement, and every measurement changes what the edge even means. If you want to talk about the end of the universe like a scientist and not like a fortune teller, you have to do something slightly annoying. You have to turn endings into parameters, not vibes, not imagery, numbers. Because every dramatic finale people love to imagine is really just one question wearing a costume. What is dark energy? If dark energy is a true cosmological constant, meaning its density stays the same as space expands, then the default future is the slow fade. Expansion accelerates forever. Distant galaxies slip away. Star formation dies down. Entropy rises. Heat death is the long, boring, brutal ending. If dark energy changes over time, then almost anything becomes possible. It can weaken, strengthen, flip sign, or behave like a field that rolls the way a ball rolls down a slope. That is why the universe's edge is not a wall in space. It is a behavior in time. So the first thing to understand is that modern cosmology has become a measurement war over a small set of numbers. The Hubble constant, which tells us how fast the universe is expanding today. The matter density, which tells us how much gravity is available to resist expansion. The equation of state of dark energy, usually written as W, which describes how dark energy behaves as the universe expands. That W number is the quiet king of the future. If W equals -1, the cosmological constant story wins. If W is less than -1, you drift toward big rip-style behavior. If W is greater than -1 but still negative, you still get acceleration but with different timing and horizons. If W evolves, the story becomes dynamic and harder to predict. The problem is, the universe does not hand you W on a plate. You have to infer it from multiple kinds of observations, and every method has its own headaches. One method uses supernovae, specifically type Ia supernovae, as standard candles. You observe how bright they appear compared to how bright they should be, and you can map distance versus redshift, basically how far versus how stretched the light is. This was the technique that first revealed accelerating expansion in the late 1990s. It is powerful, but it lives and dies on calibration. Dust, selection bias, evolution of supernova properties across cosmic time, all of it can distort the curve. Another method uses the cosmic microwave background, the afterglow of the early universe. The microwave background encodes the geometry of space and the composition of the universe at the time the first atoms formed. It is like a fossil photograph of the universe as a baby. But turning that baby photo into a prediction about the universe today requires a model that evolves everything forward. If the model assumptions shift, the inferred expansion history shifts. Another method uses baryon acoustic oscillations, basically the imprint of ancient sound waves in the distribution of galaxies. Those ripples create a preferred scale in the cosmic web. Measuring that scale at different redshifts lets you trace expansion like a ruler laid across time. BAO is one of the cleanest tools we have, but it still depends on mapping large volumes and controlling systematic errors in galaxy surveys. Then there's the growth of structure. Gravity tries to clump matter. Expansion tries to pull everything apart. The rate at which galaxies and clusters form and evolve is a direct tug of war between matter and dark energy. If dark energy gets stronger, structure growth slows earlier. If matter dominates longer, structures grow more. Measuring this involves weak gravitational lensing, redshift space distortions, cluster counts, and a lot of statistics. It is messy because the universe is messy. Baryonic physics, gas feedback, star formation, all of it contaminates the clean gravitational story. Now, here's the twist that makes the end of the universe suddenly feel like a modern thriller instead of an old textbook. Right now, some of our most important measurements disagree with each other. The Hubble tension is the famous one. When you measure the expansion rate locally using supernovae and Cepheid variable stars, you tend to get a higher Hubble constant. When you infer it from the cosmic microwave background under the standard model, you tend to get a lower value. This is not a small squabble. It is a serious mismatch that could mean hidden systematic errors, or it could mean new physics. And if it is new physics, the future of the universe could be different than the default story. Some proposed fixes involve early dark energy, a temporary dark energy-like effect in the early universe that changes the inferred calibration from the CMB. Some involve extra-relativistic particles, sometimes called dark radiation. Some involve modifications to gravity on large scales. Some involve unknown biases in the distance ladder. The point is not which one is right. The point is that the universe is currently refusing to be perfectly consistent with our simplest story. And that matters because the end of the universe is sensitive to the story we tell about expansion. If the tension is just a human mistake, then heat death remains the boring default. But if the tension is a sign that dark energy is not a constant or that gravity behaves differently on cosmic scales, then the end could be something else. Now bring back the word edge. People usually mean a spatial edge, like you fly far enough and hit a border. That is not how it works. In an expanding universe with a finite age and finite light speed, the edge is observational. It is a horizon. There is the particle horizon, the maximum distance from which light has had time to reach us since the beginning. That is the boundary of the observable universe. There is the event horizon, the maximum distance from which light emitted now will ever reach us in the future. If expansion accelerates forever, this event horizon exists, and it means there are regions that are causally cut off forever, not because of a wall, but because space expands too fast. So the end of the universe is also the end of information access. In an accelerating universe, the cosmic library slowly closes sections of itself. Pages drift beyond reach. This is why the end is not only about whether stars burn out, it is about whether the universe becomes isolated into islands of matter that cannot communicate. A galaxy group could live in its own forever bubble, with no new incoming light from beyond its horizon, and no way to send anything meaningful out. Now, some people hear that and think it sounds lonely. In physics terms, it is just causality doing its job. But it does mean something wild. The far future universe could become observationally smaller even while it is physically larger. So how do you actually decide which ending is more likely? You do not guess. You track W. You track whether W changes. You look for signatures of modified gravity. You test whether the cosmic acceleration is consistent with a cosmological constant or something more dynamic. You keep building surveys that map more galaxies, more supernovae, more lensing, more everything. This is why the story of the universe's end is not an ancient prophecy. It is a live experiment, and it has a weird emotional consequence that feels almost too poetic to be real. The universe's fate is encoded in faint patterns of light and structure that are only measurable because we exist during a special era. An era where there are still stars, still galaxies, still enough contrast in the sky to measure anything at all. In the far future, even if intelligent observers existed, their data would be worse. They might not even be able to discover the Big Bang, because the evidence would have redshifted away and the galaxies would have vanished beyond their horizon. They would live in a universe that looks static and empty, and they would be missing the context we take for granted. So yes, the end of the universe is a story about darkness and time, but it is also a story about timing in the human sense. We are early enough to see the clues. And that sets up the next part, because now the question becomes sharper. If the future depends on dark energy, and dark energy is still partly unknown, what are the best current constraints, and what would it take to actually catch dark energy changing? That is where the narrative gets interesting, because this is the point where cosmology stops being a museum and becomes a hunt. To catch dark energy changing, you do not need a bigger telescope in the usual sense. You need a longer memory, cleaner statistics, and enough independent methods that the universe cannot fool you with one single trick. Because the nightmare scenario for cosmology is not that the universe is unknowable. The nightmare is that it is almost knowable, but every measurement is just messy enough that two different stories can both seem true. A little dust here, a calibration drift there, a population bias hiding in plain sight, the kind of errors that do not look like errors until 10 years later. So the hunt is built like a courtroom case, not a magic reveal. First, you map the expansion history with multiple rulers and candles, supernovae, baryon acoustic oscillations, and the cosmic microwave background all trace distance in different ways. If dark energy is a constant, these methods should agree on the same curve once systematics are controlled. If dark energy evolves, the curve bends differently at different epochs, and the disagreement will not go away no matter how much you polish the data. Second, you measure the growth of structure as a separate channel. Expansion tells you how space stretches. Growth tells you how gravity competes. This is where weak lensing becomes a quiet superpower. You do not look for dramatic objects. You look for tiny, coherent distortions in the shapes of millions of galaxies caused by invisible mass in between. It is basically reading the universe by how it subtly bends the background. If the expansion history and the growth history match the same model, that supports standard gravity with dark energy acting like a smooth component. If they do not match, that is where modified gravity starts to smell less like science fiction and more like a serious suspect. Third, you bring in what might be the most elegant method of all, standard sirens. When two neutron stars merge, or a neutron star and a black hole, they produce gravitational waves with a signal that lets you infer distance directly from the shape of the waveform. No cosmic distance ladder, no fragile chain of calibrators. It is geometry and relativity doing the bookkeeping for you. If you can also identify the host galaxy and measure its redshift, you get a distance and a redshift in one shot. That becomes a new independent map of expansion. If it agrees with the other methods, confidence rises. If it disagrees, the tension becomes a real physical crack in the model, not a squabble over calibration. Fourth, you look for time dependence, not just a value. It is not enough to say dark energy looks like a constant today. You have to ask whether it always looked like one. That is the difference between a snapshot and a movie. A cosmological constant is a flat line across time. A dynamic dark energy field is a curve. A modified gravity theory can mimic one curve at one redshift and fail at another. So the strategy is to push measurements across as much cosmic time as possible. Near, mid, far. This is why large surveys matter so much. They are not just pretty maps, they are leverage. They give you the ability to slice the universe into many redshift layers and watch how the pattern changes as you go back in time. And then comes the ugly part that decides whether this whole thing grows up into science or collapses into clickbait. Systematics. If you want the end of the universe to be a real story and not a bedtime myth, you have to win a war against errors that look boring but kill truth quietly. You have to model dust correctly. You have to understand how galaxies evolve so you do not mistake evolution for acceleration. You have to control selection effects so you do not only observe the easiest supernovae and call it a universal law. You have to treat the interstellar medium and the instrument calibration like enemies that will exploit any laziness. This is why the most powerful phrase in cosmology is not a dramatic claim. It is consistency across independent probes. When multiple methods using different physics, different assumptions, and different data pipelines converge on the same answer, that is when the universe is not just being measured, it is being cornered. Now, connect this back to the edge of the universe idea, because here is the part most people do not realize at first. The edge is not a place you travel to. It is a limit that grows or shrinks depending on the future behavior of expansion. If acceleration continues forever, then there is an event horizon, and more of the cosmos becomes permanently unreachable over time. If acceleration weakens, the horizon changes. If acceleration reverses, the horizon changes again. The causal structure of reality is tied to whatever dark energy really is. So learning dark energy is not just learning the ending. It is learning whether the universe becomes more open or more locked down as time goes on. And once you see it that way, the stakes get weirdly personal in a cosmic sense. A future in which acceleration continues forever is a future where the observable universe slowly becomes lonelier. Not because life cannot exist, but because information and contact become harder. Galaxies outside the local group fade beyond reach. The sky becomes emptier. The cosmic microwave background redshifts into wavelengths so long it becomes effectively undetectable. The evidence of the Big Bang itself becomes harder to reconstruct. A future in which dark energy changes could keep the universe more connected, or it could do something far stranger. Some models lead to a Big Rip-style fate, where expansion becomes so aggressive that bound structures cannot hold together. Some models lead to a big crunch or a bounce if the sign flips and gravity wins again. Some models keep the long fade, but with different timing. The point is, the ending branches, and the branch is chosen by a parameter we are still trying to pin down with high confidence. That is why the modern era of cosmology feels like it is balanced on a thin edge of its own. We have enough data to see the outline of the truth, but not enough to stop arguing about the fine print. And the fine print is everything. So part 17 is the part where you stop treating the end of the universe like a poetic idea and start treating it like a measurement campaign with a deadline. Because the best era to measure the cosmos is not guaranteed to last forever. Not because the universe is going to end tomorrow. It will not. The timescales are absurdly long. The deadline is not time on a clock. The deadline is observational opportunity. We live in an era where the universe is still readable, where there are still bright markers, still contrast, still structure, still enough background light to act as a reference frame. That is not a permanent privilege. It is a window. And once you realize that, the end of the universe stops feeling like a distant doom story. It starts feeling like a mystery that is solvable only if we listen carefully while the evidence is still on the table. Which brings us to the final part. Because after all the parameters, all the probes, all the cross-checks, there is still one question left that matters more than any number. What does it mean that the universe has an edge at all, not a wall in space, but a limit in causality, a boundary in what can ever be known from any one place? That is where the story lands. Not with a scream, with a quiet, unsettling clarity. Now we can say the quiet part out loud. The edge of the universe is not a cliff in space. It is a boundary in causality. It is the line where information cannot reach you, not because it is hidden, but because the geometry of expansion makes the journey impossible within the lifetime of the cosmos as it unfolds. There are two different edges people mix together. One is the observable horizon, the farthest distance light has had time to travel since the beginning. That is like the limit of our cosmic memory. Beyond it, things may exist, but their light has not arrived yet. The other is the event horizon, which is the limit of our cosmic future. Beyond that line, even light emitted today will never reach us if expansion keeps accelerating. That second edge is the unsettling one, because it is not about how far we can see. It is about how connected reality remains over time. This is where dark energy stops being an abstract parameter and becomes the author of the universe's long-term social life. If acceleration stays close to constant, then more of the cosmos becomes unreachable, not by moving away in the ordinary sense, but by slipping outside the set of events that can ever influence us. Galaxies do not just get dim, they become causally irrelevant, not gone, not destroyed, just forever out of contact. The sky gradually empties, and the story of the wider universe becomes harder to reconstruct for any civilization living late enough. But if dark energy evolves, the ending branches. If it weakens, the universe stays more connected for longer. If it changes sign, expansion could slow and structure could dominate again. If it grows stronger in the wrong way, the expansion can become so extreme that even bound systems struggle to hold together. None of these are promised. They are just the menu of what the equations allow. The point is that the edge is not a fixed boundary. It is a living consequence of whatever dark energy truly is. And here is the weird comfort hidden inside that. A universe with an edge is still a universe with rules. It is not chaos. It is not random. It is geometry doing exactly what geometry does. Even the loneliness scenario is not a cosmic attack. It is just the universe following its own math with calm indifference. The same cold discipline that limits contact is the same discipline that lets us predict, measure, and understand. So what do we do with that as humans on a small planet? We do what science always does when reality feels too big. We turn the problem into observables, into cross-checks, into patience. We measure expansion. We measure growth. We compare independent methods until the universe runs out of excuses. We treat every dramatic claim like a hypothesis that must survive repeated contact with better data. And we remember that the most important discoveries rarely arrive as one perfect announcement. They arrive as a pattern that refuses to disappear. If you step back, the story becomes almost poetic without needing fantasy. The edge of the universe is not there to scare you. It is there to remind you that time is real, that light has a finite speed, and that the universe has a history that can be read because it is consistent enough to leave traces. Every photon you see is a message from the past. Every galaxy you map is a page in a book written long before we existed, and every improvement in measurement is a way of reading a little farther into the real structure of reality. There is also a sharper takeaway that most people miss. We live in a special era for cosmology, not because we are special, but because the universe is still readable from where we stand. The background light is still measurable. The large-scale structure is still visible. The cosmic expansion can still be traced with multiple methods. That window may not stay open forever, depending on what dark energy is. So the work matters now, not because the end is close, but because evidence is not guaranteed to remain accessible forever. So when people ask what is at the end of the universe, the honest answer is that the end is not a place. The end is a limit on connection. It is the boundary between what can ever be known from here and what will always remain outside our causal reach. And the only way to learn where that boundary truly lies is to understand the force that is stretching the universe apart. If you enjoyed this kind of story, the kind that turns a scary word into a clean idea you can hold in your mind, support the channel by liking the video and subscribing. It helps this series keep going, and it tells the algorithm that science with real stakes deserves attention.